Hello everyone. Today's topic is insertion sort. In the last two classes, we have been discussing about selection sort and bubble sort. Insertion sort is a little more efficient than bubble sort and selection sort in some practical scenarios. Basically, insertion sort is also an order of n square complexity algorithm, but in some practical setups, insertion sort is little more efficient. Insertion sort is also the pretty intuitive sorting technique. That is, this is how a person thinks about sorting. Let's look at the example of playing cards. Let's say you have this set of cards in your left hand, and you would like to sort this according to the values on the card. That is the output should be 3, 4, 6, and 9. So insertion sort, how it does is, it takes the first card out of this, that is 9, and transfers it to the right hand. So it takes each card from the left side and transfers to the right side, and while reaching the right hand side, it will insert in its proper position. Let's see it this with example. So 9 is taken and inserted at the right hand side. Next is 3. 3 is taken and inserted by looking at its correct position in the right hand side. That is, 3 should be inserted before 9. Next is 6. So 6 is taken and this should be inserted in between 3 and 9. So it will be inserted in between 3 and 9. Next is 4 is taken. So from the left hand side, each element is taken in its corresponding order, and it is inserted into the right hand side. It is inserted in the right hand side in its appropriate order based on the sorting algorithm. So 4 will be inserted here. So looking at the right hand side of your or the right hand, it is the data is sorted. So the cards are sorted. So by looking at the above example, we have done it with two hands. That is by transferring each of the cards from left hand to right hand. We can do the same thing by using only single hand. That is, the same operation can be done by using an in-place algorithm. So in the previous case, what we have been doing is in the left hand side we had an unsorted array, and in the right hand side, while transferring the elements into the right hand side, we were getting a sorted array or part of the sorted array in the right hand side. So at any particular instant of time, the left hand side was unsorted and the right hand side was sorted. We can make sure that the same thing happens here as well. That is, we create a boundary in the left hand side itself, and we say that the left side of this boundary is sorted and the right side of this boundary is unsorted. So initially the boundary will be like this, that there is nothing in the sorted part, the entire elements are in the unsorted part. Then you take the first element and you transfer into the sorted part. Because there is only one element, there is no need to compare anything, so you just transfer into the sorted part. So it is the left part of the boundary is sorted and the right part of the boundary is unsorted. Next 3 is taken and it is inserted its correct position, so that before 9, so that the left part is again sorted and the right part is unsorted. Next is 6. It should be inserted between 3 and 6. So it will look like this. Next we have 4 and should be inserted between 3 and 6. So it will look. So at the end of the day, there will be this condition, that is the right hand side of the boundary is empty and the left hand side of the boundary is fully sorted. So this is the in place insertion sort algorithm. Previously, we have seen an insertion sort algorithm which was taking extra memory. Here, the insertion sort is here. This algorithm is in place. Let's say we have 6 elements in the array, 6 integers in the array with indices from 0 to 5. So from our previous discussion about the playing cards, here we are trying to divide the array into two subsets. That is, we would like to find out a boundary, and the left side of that boundary is sorted, and the right side of that boundary is unsorted. That's what we wanted to make. Here, the array we want to divide it into two subsets. So initially we will consider one element, and initially we will say that the left side of the boundary is nil and the right side of the boundary is the entire element. Then we'll transfer each element from right side to left side, so that the left side of the boundary is sorted and the right side of the boundary is unsorted. Initially we'll take this element 7, and we can say that the 7 itself is already sorted because there is only one element. Then we can keep this boundary here, that is the 0th element is already sorted. Now we consider this element. For doing that, we create a hole here and we transfer this to this side. Let's see that. Initially all the elements till index 0 will be part of the subset, part of the sorted subset. So we have only one element, that single element is already part of the sorted subset. All the other elements are part of the unsorted subset. That is the elements at this side. So the boundary is kept here. We'll keep on picking elements from unsorted subset and we'll keep inserting them onto the sorted subset. So we'll pick 2, then we'll insert here. Then next time we'll pick 4, then insert to the sorted subset, and so on. The cells in blue color are part of the sorted subset. Next, we take out the value 2 and we keep that value in some other variable, value to be inserted. That is the value here, it was 2. That we take out and we create a hole there. Now we want to insert. Now we want to insert 2 onto the sorted part. What we do is we shift all numbers that is greater than 2 to the right hand side by one position. Here there is a hole, So we can shift the elements from left to right. So we compare this element with the value to be inserted. If it is greater than 2, then we shift it. So this is how it will look like. We'll shift 7 and the whole will be transferred to the previous location. Now there is no more elements, so you can fill 2 at that position. So it will be like this. Next element that will uses the value to be inserted is 4. Now we want to insert 4 into its sorted part. So once again we'll transfer or we'll shift all the numbers that is greater than 4 to the right hand side by one position. So 7 will be shifted, 2 will not be shifted because 2 is not greater than 4. So 7 will be shifted and that for that whole will be transferred to its previous location. So 4 will be inserted at that position. So right now the elements in shown in blue color are the sorted part, and in white color are the unsorted part. Next element that is need to be inserted is 1. So we want to shift all numbers greater than 1 to right hand side by one position. So 7 will be shifted, 4 will be shifted, and 2 also will be shifted, and the whole will be created. Whole will be shifted to this part. Then 1 will be inserted. Next element is 5. We take out 5 from that position and create a hole. Then we shift all the elements that is greater than 5. So it will be like this and we insert it. Next element is 3. We take out 3 from that position and create a hole and shift all elements that is greater than 3 to the right hand side by one position. So 7, 5, 4, all these 3 values will be shifted and 3 will be inserted at that position. Once all the elements are being shifted and when all the cells are in blue color, you can say that it is in the sorted order. We will look at the algorithm pseudocode. So we need to consider one element at a time. So that is this for loop for I is equal to 0, I less than n minus 1, I plus plus. So for when I equal to 0, we'll consider the first element. When I equal to 1, we'll consider the second element. When I equal to 3, we'll consider 2, will consider the third element, and so on. So we'll take out the value a of I. A of I value is equal to a of I means we'll take out that value and we'll say that at the ith position we have a hole now. Then while hole greater than 0, if the hole itself is at this position, at 0th position, then there is nothing to do. While hole greater than 0 and a of hole minus 1 is greater than value. So for example, if the hole is at this position and the element at this left hand side of the hole is greater than value that is need to be inserted, then we need to shift it. So that is what this condition is. While hole is greater than 0 and a of hole minus 1 is greater than that value to be inserted, then a of hole is equal to a of hole minus 1. So the hole will be shifted to left hand side, or hole equal to hole minus 1. So the element will be shifted here and hole will be shifted here. Once again, we'll compare, element will be shifted here and hole will be shifted. So once you come out of this loop to the hole where it is presently, the hole is present, we will insert the value there. So at I equal to 4, at the position when I equal to 0, we take out the element at that position. Then we'll create a hole there and we'll check all the elements that is greater than the value to be inserted here are shifted and create a hole or create a room for the current A of I. So that is insertion sort. Once again, in insertion sort, we will be dividing this set into two parts, unsorted subset and sorted subset. It will be taking each element from the unsorted. Initially, all the elements are part of unsorted subset. We'll be taking each element from the unsorted subset and inserting that element onto the sorted subset. Analysis of the insertion sort algorithm. So the analysis goes like this. This is a for loop which runs through 0 to n minus 1. So you can say that value equal to m a of I, whole is equal to I. All these statements are going to execute n minus 1 number of times, and this statement also going to execute n minus 1 number of times. This statement a of whole equal to a of whole minus 1 and whole is equal to whole minus 1. This executes maximum in the worst case. For example, here was the whole, here the whole was created and all the elements need to be shifted, so that this, for example, this was the minimum value here to be inserted, then all we need, all the elements need to be shifted. So at that, in that case, this also will be going to execute n minus 1 number of times. That is while whole greater than 0 and a of whole is greater than value. So for all the values that is available in the left hand side, this condition is true. So it will be n minus 1 into n minus 1. So it will go to n square. So in the worst case, this is going to take n square time. In the average case also, if you consider all the different cases, the insertion sort algorithm is going to take order of n square time. In the best case, the best case is that the element is already the elements in the array is already in the sorted order. So we'll consider this element, there is no shifting, this element there is no shifting, this element there is no shifting, and so on. So this while loop will not execute at all. So the entire set of instructions will be executed only in minus one time. So it is order of n time. The best case is the array is already sorted, and the worst case is the array is sorted in the reverse order, maybe the reverse order. So in the worst case or in the best case, sorry, worst case and average case, the algorithm runs in order of n square time, and in the best case, the algorithm runs in order of n time. It's an in-place sorting algorithm. As you can see, it's a stable sorting algorithm. It's an internal sort and it's non-recursive algorithm. So that's all about insertion sort. Thank you.